Hello my dear student friends, welcome you all to this again a network analysis video lecture series. In previous lecture we had a discussion about different network theorems, right? So we have studied a chapter named as network theorems, and out of those we have studied superposition theorem and Thevenin's theorem. Okay, so in this particular video lecture we shall be discussing about Norton's theorem. Okay, so in Thevenin's theorem the motto of that Thevenin's theorem is to convert a multiple resistor multiple source network to convert it into a very simplified circuit in which it will consisting of only one voltage source and one equivalent resistance. Okay, so this is the motto of that your Thevenin's theorem, right? Now the Norton's theorem is again similar kind of circuit will be there, but here you have to find out equivalent current. Okay, so this is called as Norton's current, and a parallel resistance, that is nothing but your equivalent resistance that you are going to find out as like that you have found out for Thevenin's circuit. Okay, so this is nothing but the circuit or equivalent circuit for Norton's theorem. Okay, so Norton's theorem mainly deals for equivalent current and its parallel equivalent resistance. Okay, so this is a Norton's theorem. Okay, and this is your Thevenin's theorem. Okay, so Thevenin's theorem, in which we are going to convert that particular given network into a simplified circuit in which it will have one voltage source and a series resistor, that is Thevenin's resistor and Thevenin's voltage. Okay, fine. So on the other side of your part, then the network theorem, Norton's theorem, is mainly dealing with that it is going to convert the given circuit in such a way that it will consisting of a Norton's current, right, and equivalent resistance will be connected across or parallel to this particular current source. Okay, and then you are going to connect, let us say this is again A and B terminals, then the rest of other, suppose there is a resistor, then you are going to connect that resistor, and then you may be calling that, or you are going to find out the current flowing through this, then voltage across it, then power dissipated by this particular load resistance, or for example. Okay, so like that, this is nothing but your Norton's theorem. So let us understand what is the statement of this Norton's theorem. Okay, so Norton's theorem states that any two terminal linear network consisting of number of voltage source, current source and resistances, it can be replaced by a single equivalent circuit which is consisting of a single current source. Okay, so this is nothing but your single current source, right? Suppose this is your circuit diagram, right, and in which there is a one current source and there is one voltage source. Okay, so this circuit will be simplified in such a way that it will consisting of only a single current source and a parallel resistance, that is nothing but Rn. Okay, Norton's equivalent resistance. Okay, so that single current source will have a parallel resistance with, okay, parallel with that particular resistance. How to find out then current and the resistance? Where the value of the current source is equal to the short circuit current. Now remember, in order to find out the current, we need to make the terminals A and B. Over here, we are going to make a short circuit. Okay, suppose if we are going to make an open circuit as like your Thevenin's theorem, then what is going to happen? No amount of current is going to flow, right? So we need to find out the current. Okay, because this is my intention. Okay, so ultimately we need to find out the current, and then only we can go for converting that particular circuit into the Norton's equivalent circuit. Okay, so for that, in order to find out the current, we need to make a short circuit, and in order to find out the, suppose we are finding out the Rn, so in that case, if the current source is there, you have to make an open circuit. If the voltage is there, you have to make a short circuit. Okay, fine, and A and B terminals must be left open. Okay, fine. Yes, so short circuit across the terminals A and B of the network, and the resistance. Okay, let us check out what is that. Hold on a minute. And the resistance, that is equivalent resistance, is equal to the resistance measured between the terminals with all the energy sources replaced by their internal impedances. Okay, so let us see one example. Okay, so remember that whenever we are interested to find out the current, we have to make a short circuit, and whenever we are interested to find out the resistance, we have to open circuit terminals A and B. So two steps we have to follow. First, step 1 is to find out Rn. Suppose we are finding out the equivalent resistance appearing across these terminals A and B, right? So in that case, we are going to make open circuit to the terminals A and B, and we are going to make this voltage source short circuited. Okay, so in order to make voltage, we need to make a short circuit. In order to make current is equals to 0, we have to make a open circuit. Okay, so that is the meaning of your replacing by their internal impedances, right? Okay, so over here step number 1 is what? To find Rn, open circuit terminals A and B, and replace the voltage source by short circuit, right? So this is the first step. So once I am going to do this, then the modified circuit diagram will look like this. Okay, so these are the terminals A and B. Are you getting it? So this voltage source we have made a short circuit. Okay, so that's why that voltage has become now 0. Is that fine? Now we are interested to find out the resistance seen from terminal A and B. So we are going to reduce from the other side of that terminals A and B, right? So how they are connected? 5 ohm and 10 ohm, they are connected in parallel, right? So the parallel combination is going to give me a value of Rn. So Rn is nothing but 5 into 10 divided by 15, that is R1 into R2 upon R1 plus R2. So once I am going to calculate this is going to give me a value as 3.33. Okay, so this is the first step that you have found out. Okay, so first value you have found out, that is Rn. Now let us find out how to go for finding the value of In. Okay, so as I said, this is nothing but your step number 2. To find In, short circuit the terminals A and B. So these are the terminals A and B over here, right? And we have made a short circuit. So once I am going to make a short circuit over here, what is going to happen with this? This resistor is simply getting shorted, right? That means current always chooses or selects minimum resistance path, right? So remember that this is not going to follow, or the current is not going to flow through this 10 ohm source. It is going to flow through this minimum resistance path, and that is very minimum, right? That is 0 approximately, right? Okay, so whenever we are making short circuit across terminals A and B, the resistance is going to become 0, and then ultimately we are going to find out the current flowing through this particular circuit. Okay, and that is nothing but my In, which is flowing through this short line. Okay, so let us find out In. How to find out In? Simply by using Ohm's law. So V is equals to IR, therefore R is nothing but V divided by R. What is applied voltage? Applied voltage is 20 divided by resistance is right now over here is 5 ohms only. Okay, so this is nothing but giving me a value of current, that is In, as 4 amperes. So this is the value of current In which is flowing through this circuit right now, or which is flowing through this, let us say, short circuited path. Okay, so this is nothing but the step number 2, and finally we have got two required things, that is In and Rn. So finally the circuit will look like this. It is the above circuit has been converted into In and Rn, right? So this is your In, this is your Rn, and the resistor, that whatever we have disconnected while finding out the resistance, is over here, right? And that is nothing but your 6 ohm resistance. And let us say find out the current flowing through this 6 ohm resistor. So ultimately this is your current source. This current is going to enter up to this point and then it is going to get splitted, and we are interested to find out this current, that is nothing but current flowing through the 6 ohm resistor, and that is nothing but I6. Therefore let us use the current division rule. Okay, so using current division rule, what is that? The total supplied current multiplied by opposite branch resistor, right? So 3.33 divided by total resistance present into this current dividing network. Okay, so once I am going to find out, I will be getting the value as 1.43. Okay, so out of 4 ampere current, 1.43 is going to flow from this 6 ohm resistance, and rest of other amount of current is going to flow through this 3.33 ampere, sorry, 3.3 ohm resistor, right? So likewise we are going to find out the, or we can apply the Norton's theorem to the such kind of particular circuits. Okay, so let us see one more example based on it and we'll go for the next point. Okay, now over here in this particular circuit we have one voltage source and we have another a current source, right? And terminals are mentioned over here. A is over here and B is over here, right? So remember that now you are interested to apply the Norton's theorem across the terminals A and B, right? So to find out Rn, what we need to do? We need to open circuit it. Okay, so we need to open circuit it. Fine. So let us open circuit this. So once I am going to make an open circuit over here, and I have to again open circuit this 2 ampere source, and we have to make a short circuit at 10 volt source. So ultimately let us say this is a short circuited, and then this is nothing but this resistor. Okay, okay, and what about this? This is open circuit, no? So I need to find out the resistance present between these 2 points. Okay, so remember that no amount of current is going to flow through this, so simply we can say that this is disconnected from the network. Okay, so the total or equivalent resistance present, this is nothing but 10 ohm. Okay, so as there is a no open circuit, okay, so therefore this is simply disconnected from the network. Okay, so remember that the total resistance present across the terminals A and B, or the resistance seen from the terminals A and B, will be only this 10 ohm source. Okay, this 30 ohm will not be there. Okay, so value of Rn is coming as 10 ohm. Is that fine? Okay, now let us find out In. Now for that purpose we need to go for superposition theorem. Okay, so first we'll find out the current flowing through that A and B terminals because of this 10 volt source, and then we'll go for connecting the 2 ampere source. Okay, so let us first find out the current source. In that case you have to open circuit the current source, right? So right now we are considering the 10 volt source. Okay, and the other current source we have to open circuit, right? And let us find out the current flowing through this one then. So I1 is equals to voltage, that is 10, divided by resistance, that is 10. So it is giving me a 1 ampere current which is flowing through this terminals A and B, right? Okay, and now let us consider, okay, over here we need to make a short, right? This voltage source has been shorted. This is 30 ohm resistor. This is current source, that is nothing but I think it is 2 ampere current source. Okay, what do you think, whether there is a current division rule? No, because this is a short circuit line. So as this resistor is appearing across this short, right? So what do you think, whether the current is going to flow through this? No, it will flow through this short circuit line to the ground directly, right? So that's why remember that this 2 ampere current will be appearing directly or will be flowing directly through this short circuit line to the ground. Okay, so remember that this 2 ampere current source is going to flow directly towards the ground through this short circuit line, and no amount of current is going to flow through this because it is having some certain value of resistance, that is 10 ohm, right? So remember that maximum or total current is going to flow through this short circuit to the ground. Okay, so both the currents, whether they are flowing in the same direction, we need to take the algebraic sum, right? So this I1 and I2 we need to add or subtract. We need to add because they are flowing in the same direction. This current is going to flow from up top to bottom, and this also is flowing from top to bottom, right? So we need to add these two currents. Therefore IN, that is Norton's equivalent current, is I1 plus I2, and therefore 1 plus 2 is coming as 3 ampere. Okay, so finally this is consisting of your IN and this is consisting of your RN, right? Okay, now let us let us draw the circuit. So final circuit is nothing but IN is 3 ampere, RN is 10 ohm, and finally the disconnected resistor is nothing but 20 ohm that we have connected right now. And let us find out the current flowing through this by using current division rule. So 3 multiplied by opposite branch resistor 10 ohm divided by 10 plus 20, it is coming as 30. Okay, so 1 by 3 into 3 is coming as 1 ampere. So 1 ampere is current is going to flow through this, that is nothing but I20 ohm, and 2 ampere is going to flow through this 10 ohm resistor. Okay, great. I hope you understood this Norton's theorem as well. So let us understand. I think there is next theorem is maximum power transfer theorem. Okay, fine. Let us take one more example and we'll switch to the maximum power transfer theorem. Now over here both the current sources are there. Okay, and over here the 3 ohm resistor is there, fine, and across that there are two terminals, that is terminal A and B, across which we are going to find out or we are going to apply Norton's theorem. Okay, apply Norton's theorem. So such kind of questions will be there in your final examination. Okay, so how to apply the Norton's theorem? We need to open circuit in order to find out the RN, right? We need to open circuit the current sources, as both the current sources are there. So we need to make a open circuit, and these two terminals has to be left open circuited, right? So what is this? This is nothing but a series combination of two resistors, right? So this is nothing but forming A and B, right? This wire is nothing but this one. Are you getting it? So this is 4 ohm and this is 5 ohm. So what is the value of RN? RN is coming as 9 ohm. Understood? Now for this also you need to use what? We need to use current division rule for 2 times, right? Over here we need to use current division rule, one for 10 ampere source and one for 5 ampere source. Are you getting it? Sorry. Okay, now let us find out RN. How to find out? Okay, RN we have found out. Let us find out IN. Fine. Okay, now let us consider 10 ampere current source. Okay, now A and B terminals are over here. We have to make a short circuit, right? So we have made a short circuit over there, and now we are interested to find out the current flowing through 5 or this shorted line, right? That means simply current flowing through this 5 ampere is the current simply flowing through this IN or this shorted line, right? Okay, so let us find out I5, that is current flowing through this 5 ampere current source because of this 10 ampere source. So let us use the current division rule. I is equals to 10 into opposite branch resistor divided by 4 plus 5. Okay, so 10 into 4 is 40, 40 divided by 9, it is coming as 4.44. So out of 10 ampere, 4.44 ampere current is going to flow through this 5 ohm source, right? Now let us consider the 5 ampere current source which has been connected at the right hand side. And now let us find out the current flowing through this shorted line. Is that fine? Okay, so we are interested to find out the current flowing through this 4 ohm source, 4 ohm resistor. So 5, this is nothing but the applied current multiplied by opposite branch resistor is 5 divided by 4 plus 5, right? So finally I will be getting value as 2.78, and now we need to make a algebraic addition of these two currents. One current is flowing in this direction, that is from right to left, and another current, this I1 was flowing in the left to right, that is exact in reverse manner, right? So whether we need to add it, no, we need to subtract it. So we need to find out IN finally by means of taking the subtraction of, let us say this I1 and let us say this is I2, right? So therefore 4.44 minus 2.78, that will be the value of current 1.66, that is nothing but a final value of Norton's equivalent current. Okay, so likewise we can convert the given circuit into the Norton's equivalent circuit by means of finding out the IN and RN finally. Okay, and then let us go for finally converting or finding out the value of current flowing through the disconnected resistor across the terminals AB, right? Okay, so this is nothing but the way you can apply the Norton's theorem to the given circuit. Now let us apply the maximum power transfer theorem. Okay, let us understand maximum power transfer. Okay, so remember that whenever we are applying, let us say there is a mic system, let us say there is a speaker, right, and there is an amplifier. So in order to get the maximum power to be delivered to the speaker, then we have to satisfy one criteria, that is nothing but your maximum power transfer theorem. Okay, so maximum power will be delivered to the load until if we are going to satisfy one condition. What is that condition that we are going to derive with the help of this particular theorem? Okay, so remember that the maximum power transfer theorem states that maximum power is delivered from the source to the load when the load resistance is equal to the source resistance. So this is the statement of the maximum power transfer theorem. What is the statement? The maximum power will be delivered from source, that means let us say voltage source, current source, whatever it may be. It will be delivered to the load if and only if the source resistance and load resistance are equal in magnitude. Okay, so if the values of the source resistance, let us say this is nothing but your RS, and let us say this is nothing but your RL, if the values of these two resistors are same, then and then only the maximum power will be delivered from source to the load. Okay, for example, let us say load is nothing but your speaker. Okay, so the speaker will generate or it will have the maximum power once the source resistance will be equal to this, or load resistance will be equal to this source resistance. Okay, so let us find out this condition again. Fine. So from figure it is clear that the current flowing through the circuit, this is nothing but the current, okay, is given by, what is the equation? So we know that V is equals to IR, and what is the value of R? R is nothing but, it's a series combination of these two resistors. So finally I is nothing but V, that is V supplied divided by RS plus RL. Are you getting it? And this is over here. Okay, fine. We know that what is power? Power is equals to I square RL, right? So let us represent this power in terms of V. So V square RL. Yes, this is nothing but the power. Yes, is it? So let us represent, yes, over here we are going to replace that I by V divided by RS plus RL, and it's a whole bracket square because I square is there, okay, into RL, right? This is nothing but now power. Okay, so for maximum power transfer to be delivered to the load, we can get it by taking the derivative with respect to RL. Okay, you have to take the derivative with respect to RL. Okay, and let us equate to the 0. So I think in case of your resonance also, in order to find out the maximum voltage across inductor or capacitor, in that case also we have taken the derivative with respect to that particular frequency, right? And then we have found out, or then we have equated it with 0 in order to get the maximum frequency, right? So over here also we are going to find out the maximum power delivered, okay, to the load. Okay, so that's why we are taking the derivative with respect to load, because we want maximum power at load. So for that purpose, the maximum power we can find out with respect to, if I am going to take the derivative with respect to RL, then and then only I will be getting this one. Okay, so let us take the derivative with respect to RL. Okay, fine. So again you are going to use U by V rule over here as well. D by dt of UV is equals to, what is that? V into derivative of U minus U into derivative of V divided by V square, right? Right. Okay, so that is nothing but this. Okay, so RL, if I am going to take the derivative of RL with respect to RL, then it is going to become 1. So Vs square divided by Rs plus RL bracket square will be as it is, and derivative of RL is 1 minus, now let us take the derivative of this equation. Okay, so Vs square into RL, this RL is nothing but this RL. Are you getting it? Okay, do not get confused. Okay, and 2 twice this square is going to become, it is coming at the multiplier side. So 2 into Rs plus RL, and derivative of this bracket, again it is going to become, Rs is constant, so it is going to become 0 plus 1. Okay, so therefore final equation is nothing but this. Okay, I hope you understood the derivative. You know this very well. I am not going to repeat it. Okay. Okay, now let us equate it to 0. Okay, we need to equate it to 0 in order to get the maximum value, right? So this is equal to 0, right? Let us transfer this term to the right hand side, so it is going to become a 0. Anything multiplied with 0 is going to become 0, right? So therefore Rs plus RL bracket square into Vs square minus Vs square RL, this term, let us transfer this term to the right hand side. Okay, and let us make the simplification. Fine. Okay, now let us expand this bracket and let us do the simplification. Okay, so let us simplify this. Fine. Okay, so Rs plus RL, it's a bracket square. So once I am going to transfer, it is also having a Vs square. So let us transfer this term to the right hand side. So it is going to become Vs square into RL multiplied by 2 into Rs plus RL, right? So let us cancel this bracket with this one, right? So Vs we can cancel out. Okay, fine. So Rs plus RL is equals to twice RL, right? Let us transfer this RL to the right hand side. So Rs is equals to twice RL minus RL. So this single RL will be getting cancelled out. So therefore Rs is equals to RL. This is the condition of resonance. Sorry, not resonance. This is the condition of maximum power delivered. Maximum power transfer or delivered. Okay, fine. So remember this condition for the maximum power to be delivered to the load. You will require this theorem in case of your antenna and wave propagation. Okay, that will be in the next year. Is that fine? Okay, so let us say this is one circuit in which the supplied voltage is 30 volt, supply resistor is 25 ohm, and you need to find out the load resistance. Fine, and find out how much is the maximum power delivered to the load. Okay, So what is the condition? For maximum power transfer to be delivered to the load, the condition is what? Rs must be equal to the RL. So value of Rs we know that it is 25. So 25 must be the value of RL, then and then only the maximum power will be delivered to the load. Now let us cross check whether this is really giving us a maximum power to be delivered on the load or not. Okay, so power is equals to Vs square divided by, equation of power is what? Vs square into RL divided by Rs plus RL bracket square, right? So let us find out the power. So once I am going to compute this, I will be getting a 9 watt. Okay, by using this answer also, if I am going to calculate the value of current flowing through this particular network, then I will be getting value as 0.6. So 30 is the applied voltage and 25 plus 25 is coming as 50. So 30 divided by 50 is coming as 0.6, and if I am going to compute the power, that is also giving me a 9 watt. Okay, now let us change the value of RL. If I am not going to satisfy this condition, then what is going to happen? Let us check it out. Suppose instead of taking, okay, suppose instead of taking that 25 as RL, if I am not going to satisfy this condition, if Rs is not equal to RL, then what is going to happen? Okay, so this is nothing but 25. Now let us say this is 30. Okay, and let us say this is applied voltage was nothing but 30 volt. Okay, now let us find out the current. What is the value of I? I is equals to 30 divided by 55. So definitely the value of current is going to reduce, right? So 30 by 55, let me compute it. by 55, it is coming as 0.54, okay, or 0.55. Now if I am going to compute the power, P is equals to I square R, right? RL, I square RL. So I is nothing but what? 0.55 square into 30, right? 0.55 square into 30, it is coming as 9.075. Okay, let me check it once again. Is there any mistake? Okay, let us change the value more than the 25. Let us take this as a 50. Okay, so if I am going to compute the value of current, okay, let us take this 50 plus 25 is 75. So 30 divided by 75, it is coming as 0.4. okay, and now 0.4 into 0.4 into 50, it is coming as 8. Okay, so P is equals to I square R, right? So I is nothing but 0.4 square and R is RL. RL is 50. So it is coming as less than this particular previous power, right? So previous power was 9 watt. Okay, now this is 8 watt. Are you getting it? Let us check. Now let us reduce the value of this resistor. Okay, now Rs is Rs is greater than RL. Okay, so this is the condition right now. Fine. Now this is the 30 volt source. This is Rs is 25. Now this is 10 ohm resistor. Okay, the current flowing through this circuit will be what? 30 divided by 35. Okay, so let us compute this. 30 divided by 35, it is coming as 0.85. 0.85 into 0.85 into 30 volt. sorry, 10 ohm. Yes, I square r, p is equals to I square r. I is nothing but what? It is coming as 0.85. Okay, so 0.85 square into 10. This is a square. Okay, so 0.85 into square is coming as, into 10 is coming as this 7.22. so whether this value is less than your power? Yes. Okay, so if I am going to satisfy this condition, then and then only the maximum power will be delivered. Remember this one. Okay, fine. So over here we will conclude, and we'll start in the next lecture. Okay, we'll continue in the next lecture. Fine. Okay, thank you.